Hello everyone. My name is Abanoub. I'm a PhD student at the University of Oulu, Finland. Today I'm going to talk about time series GEBA for predictive remote control under capacity limited network, which is a collaborative work with Nokia Bell Lab France. I divided my talk into 5 sections to introduce our proposed work. First, I will go for the motivation and the goal behind this work. Then I will delve into the system model. Then I will introduce the proposed work called channel-aware scheduling with GEBA. And after that, I will present the simulation result and finally conclude the work and show the next step. The wireless network control system are a specially distributed control system in which sensor, controller, actuator are decoupled and connected over wireless channels. And the remote controller associated with these robots are required to transmit high-dimensional data to the remote controller to calculate the control command and drive it to the desired states. However, we have limited uplink channel capacity to carry out this information from all these robots simultaneously. So to address this issue, we proposed that the sensor generate lower dimensional representation rather than transmitting the high dimensional data. Then the controller reason and the plane in the representation space, and after that the scheduler controls uplink channel access to select which robot transmit their representation to the remote controller. Motivated by this solution, we come up with a main novel concept called the channel-aware scheduling with GEBA. This is to select the control command and the channel allocation to satisfy the desired states for as many robots as possible under limited channel capacity. The first part of our system model is the control system, and here we consider controlling multiple different nonlinear control systems, and these dynamical systems are assumed to be unstable, and each dynamical system consisting of sensor, remote controller, and the robot, which is consisting of the nonlinear dynamic process that being controlled and the actuators that applying this control command. To stabilize this system, sensors are required to transmit high-dimensional data to the remote controller, calculate the control command, then the controller transmit this control command to the actuator to drive it to the desired states. Since each control loop is closed through the wireless channel, we have two different descriptions based on the transmission occurs or not. During a successful transmission, the actuator applying the nonlinear control policy. Otherwise, during the failure transmission, the actuator applying the predicted control command using the semantic actor model that will be detailed next. To evaluate the control performance of each robot, we utilized a customized score function, which gives a score 1 if the states of the robot is close to the desired state. Otherwise, it will give a 0 score. Here we assumed that the robot the sensor attached to the robots are generate a high traffic data volume, such as pick and place robot that associated with high frame rate camera to capture their position and orientation. For the second part of our system model is the communication system, which is crucial to closing the control loop and ensuring the control performance of each control system. Here we consider dense clutter and high base station indoor factory scenario, where we have different robots with irregular structure are randomly distributed within the coverage area of the base station. And here the sensor and the actuator are co-located and share the same transceiver, while the remote controller are located far. Here we adopted off-DMA transmission scheme with 15 kHz subcarriers, and the subcarriers are grouped into a physical resource block, and each resource block consisting of 12 subcarriers over the interval of 1 milliseconds. At each time, the robot can access the shared data channel based on the channel state information, and here the shared data channel are characterized as a bus loss and relay block fading. And at each time, the robot has availability to transmit on the available resource block, and the allocated resource block for different robots are not overlapped. Here we consider the uplink transmission from the sensor to the controller employ a fixed transmission power, then the channel capacity of the uplink transmission given as a function of the allocated bandwidth, the channel gain, and the transmission power. Then the outage probability of the uplink transmission occurs when the channel capacity to a predefined threshold. Also, to mitigate the collision during transmission when many robots are required to transmit on the same resource block, we utilize a centralized scheduler. To give at most one resource block for each robot, and the allocated resource robot for different robot is allocated resource block for different robot are not overlapped. Motivated by our challenge that we have limited uplink channel capacity to transmit high-dimensional data from many robots, we utilized Joint Embedding Predictive Architecture, or JEBA for abbreviation. This is to transmit lower dimensional semantic representation. Between different architecture of JEBA, like Pipaoy, Bootstrap Your Own Latent Architecture, and Simple Siamese architecture, we utilized Pipaoy architecture consisting of online encoder and target online network and target network. The online network consisting of online encoder and the predictor, while the target network consisting of a momentum encoder that has the same architecture of the online encoder, but with different weight, which exponential moving average weight of the online encoder. For example, here, if we have two augmented view of the same image, we feed one of them to the online network to get the predicted semantic representation, while at the same time, we feed another augmented view to the target network to get the target representation at the same time. So then we measure the MSE loss function between the predicted and target representation, and then we back propagate over the online network while we stop gradient over the target network, since our goal to just to train the online network. At this point, we can introduce our proposed approach called the channel-aware scheduling with JEBA, consisting of the TS-JEBA model to extract the lower dimensional semantic representation and predict the future semantic representation. Second is the semantic actor model to calculate the control command from this representation. Third is the channel-aware scheduling to allocate the communication resources for the robot to transmit their representation based on the channel state information. For the first component of our proposed approach, time series JEBA or TS-JEBA, we feed one augmented view at time k to the online encoder to get semantic representation at time k. Then we project this encoded data into lower dimensional space to get the semantic representation at time k. At the same time, we apply this semantic projected data conditioned with the control command to the predictor to get the semantic representation at time k plus 1. At the same time, we feed another augmented view at time k plus 1 to the target encoder to get the encoded data at time k plus 1. Then we project this encoded data to the lower dimensional space to get the projected data or the target semantic representation at time k plus 1. Then we measure the similarity between the target and the predicted representation using a cosine similarity loss function. Also, we split our model into two parts. The first part consisting of online encoder and the projector, and this will be located at the robot side to extract the lower dimension semantic representation. While the second part consisting of the online target network with the online predictor, and this is to predict the missing representation at the remote controller side. Since the semantic representation is only available at the remote controller, here the second component of our proposed approach is semantic actor model. This is to calculate the control command from this semantic representation. To train the semantic actor model, we feed the semantic representation at time k, conditioned with the desired states to the semantic actor model to get the predicted control command at time k. Then we measure the difference between them using a loss function, and then we back propagate over this model to train it. Third part is the channel-aware scheduling, and this is since our focus lie on designing the uplink scheduling variable to select which robot transmit their representation to the remote controller, and this is to enhance the control performance for as many robots as possible under limited channel capacity. We come up with the channel-aware semantic scheduling. This is to maximize successful transmission probability for all robots under scheduling constraint to mitigate the collision during transmission, and also the communication constraints to ensure reliable transmission. At this point, we would like to investigate our proposed approach through end-to-end control in a simulator through 4 steps. First, we collect the data and creating the dataset consisting of camera frames and the control command. Second is the data pre-processing, including image augmentation and normalization. Third, we build the TS-JEBA model consisting of online and target network, and also the semantic actor model. Finally, we train and test the TS-JEBA and semantic actor model. For the first step, data collection and creating a dataset, we utilized here the inverted cart ball system. And the dataset of inverted cart ball system consisting of camera frame along with its control commands. The frame in this dataset come from a camera with a frame rate 1 frame per second and the frame resolution 1200 by 600 pixels, and the trajectory length is 100 seconds. And each trajectory here is initiated from random initial condition with uniform distribution and different desired state. Then the training dataset consisting of 20,000 pairs of camera frame along with their control command. For the data pre-processing, we apply image augmentation. This is to increase the diversity of our training dataset. So we apply the color jitter transformation by changing brightness, contrast, saturation, and hue, and also we apply grayscale transformation. Also, we resize each frame to 640 by 128 pixels, and also apply normalization for each frame, and also the control command using z-score normalization. As we can see here, we show the CDF of the mean absolute percentage error between consecutive frame with different frame rate with and without image augmentation. Without image augmentation, we can see as we decrease the frame rate, the temporal correlation between consecutive frames start to be low. This is highlighting that the input data for our TSGBA models are temporally different. After we apply the image augmentation, we can see the mean absolute percentage error range between the consecutive frames start to be large, ensuring the spatial correlation between consecutive frames is temporally especially low. And also for that, we choose 1 frame per second with image augmentation. This to increase the diversity of our training dataset and ensure also our TSGBA models generalize well. For the third steps to build the TSGBA model, here consisting of the online network and target network. The online network consisting of the online encoder, which have the same architecture of FreeNet 18, but with some modifications and output size of 512. Then we apply this encoded data to the projector, which is represented here by multi-layer perceptron and output dimension 256. Then we apply this projected data to the predictor, which is represented by multi-layer perceptrons and conditioned with the control command and the output dimension 256. For the target encoder and the projector, they have the same architecture of the online encoder and the online projector. Then we train and test the TSGBA model using the following parameter, including the cosine similarity loss function, applying weight decay, applying also linear scheduling. This is to ensure the stability of training this model and also ensure that our model generalize well. Here we would like to analyze the obtained semantic representation come from the encoder and the predictor of our trained model using the Tesny analysis. Here we show the first two components of the Tesny analysis, which explain 94% of the variance in the data. As we can see here, that the Tesny component show a clear separation over the range of -80 to 80, indicating that we can extract the semantic structure within the frames and also learning a meaningful representation without collapsing to a naive solution. Second, we would like to investigate the encoder of our TSGBA model. So we apply two images with different color but have the same states to the encoder of the TSGBA model. And as we can see that the encoder maps the two image or high dimensional data to the same representation. This is highlighting that our encoder can capture the semantic representation respective to the color diversity. In contrast, when we feed two images with different color and have the same states to the encoder of the generative autoencoder model, it can map them to two different representations, highlighting that the encoder of the generative models can't capture the semantic representation and also lacking of using this representation for the downstream task unless we apply the decoder to reconstruct the original image and utilize it for the downstream task, which is exponentially expensive. Fourth is to train and test the semantic actor model, which is nonlinear evaluation for the TSGBA model. At the first, we extract the number of features from the last layer of the projector. Then we add the semantic actor model with input size equal to the number of extracted feature and output size is action dimension. Then we create a label dataset for training and testing the semantic actor model consisting of the semantic representation along with its control command. Then we train semantic actor model using the following parameter, including mean absolute percentage error loss function. Then we test the trained semantic actor model using the normalized mean absolute error between the predicted and the control command. Here's the semantic actor model consisting of two hidden layers with input representing the semantic representation come from the projector and concatenated with the desired states. And the output is representing the control command. Once we trained the TSGBA and semantic actor model, we can evaluate our model through end-to-end control in a simulator. Here in this figure, we would like to evaluate the encoding and the predicting capability of the TSGBA model. Compare it to the baseline. And here we compare it with normalized control prediction error, communication bits per step, and normalized score over the prediction horizon. For the encoding capability of our proposed TSGBA model, we compare it with the optimal control using a nonlinear control theory and supervised model using 2 and 4 consecutive image, and also generative actor model using 2 consecutive image. As we can see, our proposed approach can achieve a low normalized control prediction error compared to the baselines, which yielding an acceptable normalized score over the prediction horizon compared to the baseline. And also this is with a minimum communication bits. This highlighting that our proposed approach can accommodate a large number of robots under limited channel capacity and without compromising the control performance. In contrast, the baselines can achieve almost the same normalized score value, but at the cost of utilizing high communication bits. For the predicting capability of the TSGBA model, we compare it with the baselines with zero action and repeated action. As we can see, the baselines can keep an acceptable normalized score for at most 6 times step ahead. And also this is come at the cost of utilizing a high communication bits. In contrast, our proposed approach can keep a normalized, acceptable normalized score for up to 15 times step ahead, but with minimum communication bits. And this as well highlighting that the proposed approach can accommodate a large number of robots without the compromising the control performance. As an ablation study, we would like here to show the impact of changing the projector output dimension on the normalized control prediction error, communication bits, and also normalized score over the prediction horizon. As we can see, when we decrease the projector output dimension, the normalized control prediction error start to be increased while the communication bits decrease. And this is also affecting on the normalized score. Hence, we would like to ensure that we achieve an acceptable normalized score with minimum communication bits. In the last slide, we would like here to conclude that since our goal is to enhance the control performance under limited uplink channel capacity, we utilized channel-aware scheduling with GBA, consisting of TSGBA to extract lower dimension semantic representation and predict the future representation, semantic actor model to calculate the control command from this representation, and the channel-aware scheduling to select which robot transmits their representation based on the channel state information. And this is to efficiently utilize our communication resources to accommodate as many robots as possible without compromising the control performance. But however, this has come at the cost of utilizing high computational resources to train this kind of model. As a future work, since we here designed independent control system, we plan to design a collaborative robot to satisfy a global goal. Thanks for your attention. This is the end of slides. I'm happy to answer your question. Yeah, thank you.